In 1991, this continuous camera glide across a classical ballroom floor solved a severe limitation in film animation. Before this, cell animation was bound to flat planes. A camera could pan horizontally, but moving deep into a space meant fighting the constraints of a static, painted background. Simulating a tracking shot required artists to manually redraw the environment frame by frame, estimating how the perspective of every arch and pillar should warp as the viewer moved. The Walt Disney Computer Animation Production System circumvented this. It allowed a virtual camera to dolly and sweep continuously around hand-drawn, two-dimensional character cells. Driving those calculations was the hardware, Silicon Graphics personal iris workstations, running at 33 MHz to process complex spatial geometry. This diagram shows the raw data the computer evaluated. A 3D wireframe mesh of a 72-foot domed ceiling and a chandelier defined every coordinate of the environment. Generating the illusion of depth requires pushing every one of those vertices through a strict mathematical pipeline of matrix transformations to simulate physical perspective. Realizing true cinematic depth on a flat screen relies on the unyielding rules of the coordinate space pipeline. This diagram isolates the chandelier in object space. Here, vertices only understand their local position relative to their own center point. These raw points have no mathematical concept of where the viewer is located or what exists around them. To build a spatial relationship, the rendering engine applies the view transform matrix. This animation shows the vertices multiplied by that matrix, entering camera space. The camera acts as the absolute origin point. In this left-handed convention, positive z points directly into the screen, positive x points right, and positive y points up. The geometry is now oriented to the camera lens. However, the projection is still orthographic. It is perfectly flat and lacks any true perspective scale. This diagram introduces the view frustum, the geometric boundary that defines exactly what the virtual camera can see. The horizontal and vertical field of view angles dictate the specific width and height of this pyramidal volume. At the front, the pyramid is sliced off by the near clip plane. This plane is a mathematical necessity. If geometry passed exactly through the camera origin, the system would divide by 0 and trigger a fatal error. At the back end, the far clip plane caps the pyramid, mapping to the absolute maximum depth value the system's buffer has the memory to store. Any geometry falling outside these bounding planes is mathematically discarded, ensuring processing power is only spent on visible objects. We have successfully isolated the visible world into a bounded box, setting the stage for the crucial compression into two-dimensional space. This diagram displays the 4x4 clip matrix. This is the core mathematical engine that forces the 3D world to obey the laws of human perspective. Its first function scales the x and y coordinates based on the camera's zoom parameters. The crucial mechanism is located in the fourth column, containing the specific values 0, 0, 1, 0. This column converts the data into a 4D homogeneous coordinate. It copies the precise z depth into a new fourth variable called w. Multiplying by this matrix does not project the image or create the depth. It only prepares the variables. This equation shows the perspective divide, a step hardwired directly into the rendering hardware. The hardware converts the 4D vector back to 3D by actively dividing the x, y, and z components by that new w variable. Because w holds the exact z depth, the object's distance from the camera literally becomes the mathematical divisor. Dividing x and y by a massive w value, meaning the object is distant, forces those coordinates into a drastically smaller position on screen. Conversely, dividing by a tiny w value leaves the x and y scales of close objects physically large. Simultaneously, this division morphs the entire pyramidal frustum into a normalized, perfect mathematical cube space. The homogeneous divide is the exact mathematical mechanism that enforces physical, Lambertian-like perspective size decay on a two-dimensional screen. This diagram shows the final pipeline step, mapping the normalized cubic space to the literal pixels of the display device. Equations use the display's exact width and height to assign every remaining vertex a definitive x and y pixel coordinate on the monitor. Applying this complete pipeline back to the 1991 ballroom, the 86 by 126-foot dome grid was fed continuously through this exact perspective divide. The perfectly foreshortened background geometry provided a flawless two-dimensional foundation for the animators. During the compositing phase, the hand-drawn cells of Belle and the Beast were seamlessly layered atop this mathematically shifting 3D projection. This hybrid technique demonstrated that algorithms, executing millions of localized spatial divisions per second, enabled the simulation of cinematic reality in animation. There is one critical addendum. While positional vertices survive this pipeline flawlessly, surface normals require special treatment. This diagram isolates a surface normal, a covariant directional vector, pointing perpendicularly outward from the geometry. These are essential for calculating physical radiometry and lighting. If a non-uniform scale transformation is applied during the pipeline, the normal vector breaks its perpendicular alignment and distorts. To fix this, graphics engines must multiply the normals by the inverse transpose of the model matrix, restoring accurate perpendicularity. Without this exact correction, physical lighting models, like the rendering equation, fail entirely. Photorealistic worlds emerge from the rigorous, invisible execution of linear algebra.